All right, class. So in this lesson, we're going to move on with probability distributions, but this time we're going to look at how we calculate various measurements of probability distributions. So like various quantities like mean, variance, standard deviation. We're going to talk about what they mean. So if you recall, in the last quarter, we calculated the average, standard deviation, and variance for values in a data set. So now we're going to look at, probability distributions in those quantities. So if you know how to calculate mean, standard deviation, and variance of a random variable, you should be all set for this lesson. All right, so remember what the mean is. The mean is a measure of center. And what that means is that it measures the middle of a data set. So it measures what is considered to be a typical value in the long run. So in order to calculate that, we're going to use this formula for the mean. Remember that the mu stands for the theoretical mean. This is for your sum. Remember that x is what we use for our random variable. And then the p is used for probability. Alright, so all we got to do is basically multiply our random variable with its chance of occurring and then add these together. So to calculate the mean, you need to be able to construct the probability distribution like we did in the lesson 1. You also have to know how to determine the sample space, and these go hand in hand together. So you need the sample space essentially to find the probability distribution. Alright, so once you do that, we can make the calculations. Alright, so what we're going to do is we're going to look at the mean number of heads when you toss 2 coins at once. So in order to do that, we need to look at the sample space for a 2-coin toss. So you can have both heads, heads, tails, tails, heads, or tails, tails, and that is your sample space. Alright, so we're going to basically construct our probability distribution. So we can have 0 heads, 1, 2, and that's it. 0, 1, or 2, because we're only tossing 2 coins. So the probability of getting no heads at all is basically getting all tails. So that's 1 out of 4. For getting 1 heads, well, that's 2 choices. So that's 2 out of 4, which is 1/2. And then the last one's 1/4. Alright, so that's a probability distribution. So we need to go ahead and calculate our mean. So we need to take our random variable, so we have 0. So basically we multiply these guys together, x times p of x. So we have 0 times 1/4, we have 1 times 1/2, and we have 2 times 1/4. 0 times 1/4, that's 0. We have 1 times 1/2 is 1/2. 2 times 1/4 is 2/4, which is 1/2. And then 1/2 plus 1/2 is 1. So the mean is equal to 1. So basically that means that in the long run, meaning that the more trials we do of this where we toss 2 coins at once, so if we keep continually doing this forever, if we average out all our trials, we should get 1 heads on average. Alright, so in the long run, we will get an average of 1 heads. Alright, so let's go ahead and do the same thing for a die roll. So we're looking at the mean of the number of spots that appear. So x is the number of spots. So we have 1 through 6. And each of those possibilities or outcomes is attached to a probability of 1 out of 6. So in this case, the mean is quite simple. We just multiply the x times the 1 out of 6, and we do that for all of them. Alright, so we have 1 times 1 out of 6 is 1 out of 6. 2 times 1 out of 6 is 2 out of 6. 3 out of 6, 4 out of 6, 5 out of 6, and 6 out of 6. So we're going to go ahead and add these together. Remember, we have a common denominator of 6. And we have 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, 10 plus 5 is 15, plus 6 is 21. So we got 21 out of 6. 21 out of 6, 3 goes into, or 6 goes into 21 3 times. 6 times 3 is 18. And then we have a remainder of 3. So that's the same thing as 3 and 1/2, which is 3.5. So that is our mu. That's our theoretical average. So on the long run, if we keep doing this, if we keep rolling the die, right, forever, and we average the number of dots, we're going to get 3.5 dots. So that's what that means. Now in number 3, we're looking at a 4-children family. So if we keep having 4-children families, how many of those on average will be girls? All right, so we need to go ahead and do our sample space. How many possibilities are there? Well, remember by the fundamental counting theorem that we can multiply the number of ways together to get our total number of ways. So here we have 4 slots for 4 children. We can get a boy or girl. There's 2 ways of doing that. 2 ways of getting the next child, 2 ways of getting boy or girl, and so on. We multiply those number of ways together by the fundamental counting theorem or principle, and we get a total of 16 different families that can be formed. Alright, so what we're going to do is we're going to list out all of those families, 4 children families. Alright, so first option we have all boys, one girl, girl as a second child, girl as a first child. Alright, that exhausts all the possibilities of 1 girl. So now let's look at 2 girls in the family. Two, 4, 6, 8. That's 8 so far, so we're halfway there. Two girls in the middle. Girl, boy, girl, boy. Girl, girl, boy, boy. So that's all the possibilities of having 2 girls. Now let's do 3 girls. Girl, boy, girl, girl. Girl, girl, boy, girl. Girl, 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 boy, and then all girls. So that's a total of 16. That is our sample space. Alright, so now we can go ahead and calculate the probabilities here. So we could do our probability distribution. So we can have 0 girls, 1, 2, 3, or 4. So what's the probability of getting 0 girls? Alright, there's only one way of getting 0 girls, and that's getting all boys. So that's 1 out of 16. Alright, what's the probability of getting 1 girl? Well, we have 1 here, 2, 3, and 4. So we got 4 ways of getting 1 girl. So that's 4 out of 16, which is 1/4. Okay, how many ways of getting 2 girls? Well, there's 1, 2, 3, 4, 5, and 6. So that's 6 out of 16, which that reduces to 3. Or I'm sorry, that divided by, we need to divide by 2, so that reduces to 2 8s. Okay, so that right there is a 2. Let me rewrite that. So 2 8s. What about 3? Yeah, we have 1, 2, 3, and 4. Alright, so that's 4/16, which is 1/4. And then the last one, there's only one way of doing that. Alright, so then we can go ahead and calculate the mean. So we are going to simply multiply these guys. So 0 times 1/16, 1 times 1/4, which is the same thing as 4/16, 2 times 2/8. 2/8 was the same thing as, wait a second, that doesn't make sense. This is 4/16. Times 2 times 2, this is that 4/16? I think I messed this up here. That's 2/8. 1, 2, 3, 4, 5, 6. 6/16 is the same thing as divide by 2, divide by 2. This should be 3/8. That's my bad, guys. This right here is not 2/8, it's 3/8. There you go. I knew there was something iffy about that. Alright, so now we have 3/8, which is the same thing as 6/16. We have 1/4, which is the same thing as 4/16. And then we got 4 times 1/16. The reason why I do it in terms of 16 is because it's easier to add the fractions at the very end. So we got, this is 0. 1 times 4/16 is 4/16. 2 times 6/16, that's 12/16. We have 3 times 4 is 12/16. 4 times 1, so it's 4/16, and then we can add the numerators together. It makes it easier that way. Actually, we can reduce this now. That probably makes it easier. So this is 1/4. 12/16 is the same thing as 3/4. We got 3/4, and then we got 1/4. That's definitely easier to add. So we got 3 plus 1 is 4, plus 3 is 7. So we got 8/4, which is 2. So on average, it looks like you're going to get 2 girls, which kind of makes sense, 2 boys, 2 girls. So that does make sense. So if you keep doing this infinite amount of times, you're going to get on average 2 girls. All right. So now we're going to look at variance and standard deviation. So remember that variance and standard deviation gives you information about the spread of the data, whereas mean and mode and all that stuff, that gives you the information about the mean or about the middle or center of the data set. All right, so in order to calculate this, you're going to use the following formulas. All right, so remember, the variance is given by sigma squared. So this is the theoretical variance, or just the variance. And then remember that this is your standard deviation. Remember that the standard deviation is the square root of the variance, always. All right, the standard deviation is always going to be the square root of the variance. So when calculating these guys, what I like to do is I like to employ a method where I make a table with columns. All right, so I like to do the columns labeled x, p of x. This is for your probability distribution, and then I like to include the x times p of x. Oops, before I do that, I like to do the x squared. So I like to do the x squared, and then x times p of x, and then the last one is x squared times p of x. Okay, so that's what I like to use when I calculate the variance and standard deviation. All right, so we're going to go ahead and do this for example 2. So example 2, remember that was the number of spots when a die is tossed. Okay, so we're going to do the same chart. So we have x, we have p of x, so we have 1 through 6. We have our probability. Okay, we're going to do our x squared. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36. Now I like to do the x times p of x. So that means I'm going to multiply the first two columns. So 1 times 1 out of 6 is 1 out of 6. Then we have 2 out of 6, 3 out of 6, 4 out of 6, 5 out of 6, and then 6 out of 6. Alright, and then we have our x squared times p of x. So 1 times, so we're going to multiply these two columns here. So 1 times 1 out of 6 is 1 out of 6. 4 times 1 out of 6 is 4 out of 6. 9 times 1, 9 out of 6. 16 out of 6. 25 out of 6. And then 36 out of 6. Alright, so now what we can do is we can basically find the mean, which is mu, and then we can find the x squared times p of x. So in order to do that, we need to be able to find the total for these two columns. So the sum of x times p of x. We actually already did that. If you look at number 2, we already did that when we calculated the mu here. So that gave us 3.5. So that's 3.5. So we're just going to write this as 3.5. Alright? Alright, so now we're going to have to do the sum of x squared times p of x. So we have to add up all of these guys. Alright, so we got 36 plus 25 plus 16, all that stuff. So I'm going to do that on the calculator real quick. So we got 36 plus 25, that's 61. 61 plus 16 is 77, plus 9, plus 4, plus 1. So that gives me 91 out of 6, which is 6 goes into 91 15 times, and with a remainder of 1. So this is about 15.17. Alright, 15.17. We'll round it to 15.2. So let me round it to 15.2 just to make it a little bit easier. Alright. So now we're going to go ahead and plug it into the formula. So we have sigma squared equals sigma x squared p of x minus mu squared. So we're going to go ahead and take our x squared p of x, which we said was about 15.2, and we're going to minus it by our mu squared, which is 3.5 squared. Alright, and then we're going to go ahead and figure out what that number is. And that will give us 2.95. Let me go ahead and make sure that's correct here. Okay, so approximately 2.95. And then, so that's our variance. That takes care of that. And then our standard deviation is going to be the square root of that guy. So square root of 2.95, that's about 1.72. Alright, so those are our two answers. And what that's telling us is that's basically saying, remember, this is spread. This is a measure of spread, right? So this is saying on average, right, if we keep doing this in the long run, on average, basically the number of dots that we see is going to be different from the mean by about 1.7 dots, okay? So this is approximately 2. So this is saying in the long run, the number of dots that we get, if we average it out, is going to be somewhat different from the average of 3.5 by about 2. So some days we might get 5.5. Sometimes we might get, less than that. So that's given by this guy. This is telling us how spread out it's going to be. Alright, so then the last example I believe for variance and standard deviation. So we have a probability distribution, and it looks like X stands for the number of telephone lines. So we have 4 telephone lines. Actually, it stands for, it says the probability that 0, 1, 2, 3, or 4 people will get through. So X is the number of people that will get through, and then P is the probability. So they want us to find the variance and standard deviation. So we are going to go ahead and include our other columns here. So we have, since we have X and P of X, I'm not going to repeat it here. I'm just going to go ahead and do X squared. I'm going to do X times P of X. And I'm going to do X squared times P of X. So X squared is 0, 1, 4, 9, and 16. X times P of X. So we're going to multiply these two. So we get 0. 1 times 0.34 is 0.34. 2 times 0.23 is 0.2 or 0.46. 3 times 0.21 is 0.63, and then 4 times 0.04 is 0.16. X squared times P of X, so we're going to multiply X squared with the probability, so this is going to be 0. 1 times 0.34 is 0.34. 4 times 0.23, that's going to be 0.92. 9 times 0.21 is going to be 1.89. 4 times 16 times 0.04. So 16 times 4, that should be 64. So this should be 0.64. I'm going to verify that with you guys. So 4 times 16. Okay, so now we're going to go ahead and add this together. So we have 0.34 plus 0.46 plus 0.16, so this is going to be 1.59. And this is our mean, so this is mu equals, so we got our average already. Now we're going to go ahead and find our X squared P of X. And that gives us 3.79. So now we're going to go ahead and do our sigma squared, which is the X squared times P of X minus our mu squared. And that gives us 1.26 approximately. Alright, and then sigma is going to be the square root of that guy. Which is approximately 1.12. Alright, so then it's asking, should the station have considered getting more phone lines? So we know that on average, we're going to get about 1.59 phone lines, which is around here, right? If where this line is, so about 1.59. So it's sort of halfway. And what happens is, we know that on any given day, it could spread out by about 1.12. So it could spread out by 1.12 on each side, or on very rare occasions, it can spread out by more than 1.12. All right, so we can add plus 1.12. We can have another 1.12 spread, but that is very rare. So on most occasions, we should be fine with having 4 phone lines, because usually the most that it will spread to is about this guy, which is 1.59 plus that's still less than 4. So that means that we have plenty of phone lines. There's a very rare chance that we'll need more than 4 lines. Okay, so we are going to say no, we should not get more than phone lines. There is a small chance of getting more than 4 calls. All right. Okay, so now we're going to talk about what expectation is. All right, so the expected value. So the expected value is actually not something that is new. So we've already kind of talked about it. In order to calculate it, you're going to actually find the long run average. All right, so you're going to find the theoretical average. Theoretical average or long run average. Alright, so this is basically the value that you expect to get over the long run, which makes sense, which means it's the typical value of the variable, which means that you're going to calculate the mean. Alright, so notice that it has the same formula as the mean. So because it gives you an idea of that typical value over the long run. So how do we, so what we generally use this for is generally for gambling or games. So like if you're playing a game or if you're gambling, what are the chances of, that you, or like what is the typical expectation that you're going to get? So like what, on average, what am I going to expect to get from this game? Am I going to expect to lose? Or am I going to be expected to gain some money? Or something like that. All right, so that's where this actually does help. So for number 5, we're looking at 1,000 tickets are sold at $1 each, and you're playing for a color television that is valued at $350. So what is the expected value of the game? So if you participated in this game or in this event, what do you expect to get on average? All right, so basically we got to come up with a probability distribution. So we're going to list out our possibilities. So you're only buying one ticket, so that means you're paying $1. All right, so the first option, the first possibility is that you pay for a ticket and you end up being short $1. All right, so you can expect to lose $1. All right, so negative $1. All right, and that's if you pay for a ticket and you don't get the television. Right? So now if the second option is you pay for a ticket and that becomes the winner. So you either win or lose. So the second option, you win. If you win, well then you have a net earnings of $349 because you get the $350 television, but you paid $1 for the ticket. All right, so those are your two options. All right, what's the probability of losing the $1? Well, there's 1,000 tickets here. So that means that there's only one ticket that's the winner. So that means you have 999 tickets that are losing tickets out of 1,000. There's only one ticket that's the winner. All right, so that's your probability distribution. All right, so then what's the expectation? What do I expect to get out of this? Am I going to expect to win, or am I going to expect to be losing on average? So that's where the mu comes into play. So that's where we use E of x. So E of x stands for expectation. All right. So we're going to calculate this. We got the -1 times the probability. And then we have 349 times the probability. All right, so we have -1 times 999, so that's -999. 349 times 1 is 349. So it looks like we're going to do -999 plus 349. And that's going to give us -650 out of 1,000. All right, and then if we convert that to like a decimal or something, 1, 2, 3, that means that's going to be -0.65. All right, and what that's saying is that on average, you are expected to lose 65 cents from this game. On average. All right, so most of the time you're going to be losing $1, $1, $1, but then at one point you may get the television, so that's $350. So then on average, it averages out that you end up losing 65 cents. All right, so overall, this is not a very good game to do. You're expected to lose. So then in that case, that's not fair, right? So when we're talking about gambling, if the expected value is 0, the game is said to be fair. That means that on average you're not expected to gain anything, but you're also not expected to lose anything, so it's considered fair for both parties. However, if the expectation is positive, that means the game is in the favor of you as the player. So you get something out of it, so that's in favor for you. If the expected value is negative, then the game is not in your favor. It's actually in the favor of the house, the other side. All right. But when it balances out on both sides, it becomes fair. All right. And that's where we can use expected value. So we talked about expected value, we talked about standard deviation and variance, and we talked about theoretical average.